Hello and welcome to my YouTube channel. My name's Akashveer and I am reading A Brief History of Time written by Stephen Hawking. This is chapter number 10, The Unification of Physics. As we explained in the first chapter, it would be very difficult to construct a complete unified theory of everything in the universe all at one go. So instead we have made progress by finding partial theories that describe a limited range of happenings and by neglecting other effects of approximating them by certain numbers. Chemistry, for example, allows us to calculate the interactions of atoms without knowing the internal structure of an atom's nucleus. Ultimately, however, one would hope to find a complete, consistent, unified theory that would include all these partial theories as approximations, and that did not need to be adjusted to fit the facts by picking the values of certain arbitrary numbers in the theory. The quest for such a theory is known as the Unification of Physics. Einstein spent most of his later years unsuccessfully searching for a unified theory, but the time was not ripe. There were partial theories for gravity and the electromagnetic force, but very little was known about the nuclear forces. Moreover, Einstein refused to believe in the reality of quantum mechanics, despite the important role he had played in its development. Yet it seemed that the uncertainty principle is a fundamental feature of the universe we live in. A successful unified theory must therefore necessarily incorporate this principle. As I shall describe, the prospects for finding such a theory seem to be much better now because we know so much more about the universe. But we must be aware of overconfidence. We have had false downs before. At the beginning of this century, for example, it was thought that everything could be explained in terms of the properties of continuous matter, such as elasticity and heat conduction. The discovery of atomic structure and the uncertainty principle put an emphatic end to that. Then again in 1928, physicist and Nobel Prize winner Max Born told a group of visitors to Göttingen University, "Physics, as we know it, will be over in 6 months." His confidence was based on the recent discovery by Dirac of the equation that governed the electron. It was thought that a similar equation would govern the proton, which was the only other particle known at the time. And that would be the end of theoretical physics. However, the discovery of neutron and the nuclear forces knocked that one on the head. Having said this, I still believe there are grounds for cautious optimism that we may now be near the end of the search for the ultimate laws of nature. In previous chapters, I have described general relativity, the partial theory of gravity, and the partial theories that govern the weak, the strong, and the electromagnetic forces. The last three may be combined in so-called Grand Unified Theory, or GUTs, which are not very satisfactory because number of quantities like the relative masses of different particles that cannot be predicted from the theory but have to be chosen to fit observations. The main difficulty in finding a theory that unifies gravity with the other forces is that general relativity is a classical theory. That is, it does not incorporate the uncertainty principle of quantum mechanics. On the other hand, the other partial theories depend on quantum mechanics in an essential way. A necessary first step, therefore, is to combine general relativity with the uncertainty principle. As we have seen, this can produce some remarkable consequences, such as black holes not being black and the universe not having any singularities but being completely self-sustained and without a boundary. The trouble is, as explained in chapter 7, the uncertainty principle means that even empty space is filled with pairs of virtual particles and antiparticles. These pairs would have an infinite amount of energy, and therefore, by Einstein's famous equation E equals mc squared, they would have an infinite amount of mass. Their gravitational attraction would thus go up the universe to infinitely small size. Rather similar, seemingly absurd infinities occur in the other partial theories, but in all these cases, the infinities can be cancelled out by a process called renormalization. This involves cancelling the infinities by introducing other infinities. Although this technique is rather dubious mathematically, it does seem to work in practice and has been used with these theories to make a prediction that agree with observations to an extraordinary degree of accuracy. Renormalization, however, does have a serious drawback from the point of view of trying to find a complete theory, because it means that the actual values of the masses and the strengths of the forces cannot be predicted from the theory, but have to be chosen to fit to the observations. In attempting to incorporate the uncertainty principle into general relativity, one has only two quantities that can be adjusted: the strength of gravity and the value of the cosmological constant. But adjusting these is not sufficient to remove all the infinities. One therefore has a theory that seems to predict that certain quantities, such as the curvature of space-time, are really infinite. Yet these quantities can be observed and measured to be perfectly finite. This problem in combining general relativity and uncertainty principle had been suspected for some time, but was finally confirmed by detailed calculations in 1972. 4 years later, a possible solution called supergravity was suggested. The idea was to combine the spin 2 particle called the graviton, which carries the gravitational force, with certain other new particles of spin 3 by 2, 1, 1 by 2 and 0. In a sense, all these particles could then be regarded as different aspects of the same superparticle, thus unifying the matter particles with spin 1 by 2 and 3 by 2 with the force-carrying particles of spin 0, 1 and 2. The virtual particle-antiparticle pair of spin 1 by 2 and 3 by 2 would have negative energy, and so would tend to cancel out the positive energy of spin 2, 1 and 0 virtual pairs. This would cause many of the possible infinities to cancel out, but it was suspected that some infinities might still remain. However, the calculations required to find out whether or not there were any infinities left uncancelled were so long and difficult that no one was prepared to undertake them. Even with a computer, it was reckoned it would take at least 4 years, and the chances were very high that one would make at least one mistake, probably more. So one would know one had the right answer only if someone else repeated the calculations and got the same answer. And that did not. Despite these problems and the fact that the particles in the supergravity theories did not seem to match the observed particles, most scientists believed that supergravity was probably the right answer to the problem of the unification of physics. It seemed that the best way of unifying gravity with the other forces. However, in 1984, there was a remarkable change of opinion in favor of what are called string theories. In these theories, the basic objects are not particles which occupy a single point of space, but things that have a length but no other dimensions. Like an infinitely thin piece of string, these strings may have ends, so-called open strings, or they may be joined up with themselves in closed loops, called closed rings. A particle occupies one point of space at each instant of time, thus its history can be represented by a line in space-time, the world line. A string, on the other hand, occupies a line in space at each moment of time, so its history is space-time in a two-dimensional surface called the world sheet. Any point on such a world sheet can be described by two numbers, one specifying the time and the other the position of the point on the string. The world sheet of an open string is a strip. Its edges represent the paths through space-time of the ends of the string. The world sheet of a closed string is a cylinder or tube. A slice through the tube is a circle, which represents the position of the string at one particular time. Two pieces of strings can be joined together to form a single string. In the case of open strings, they simply join at the ends, while in case of closed strings, it is like the two legs joining on a pair of trousers. Similarly, a single piece of string can divide into two strings. In string theories, what were previously thought of as particles are now pictured as waves traveling down the string, like waves on a vibrating kite strings. The emission or absorption of one particle by another corresponds to the dividing or joining together of strings. For example, the gravitational force of the Sun on the Earth was pictured in particle theory as being caused by the emission of a graviton by a particle in the Sun and its absorption by the particle in the Earth. In string theory, this process corresponds to an H-shaped tube or pipe. String theory is rather like plumbing in a way. The two vertical sides of H corresponds to the particles in the Sun and the Earth, and the horizontal crossbar corresponds to the graviton that travels between them. String theory has a curious history. It was originally invented in the late 1960s in an attempt to find a theory to describe the strong forces. The idea was that particles like the proton and the neutron could be regarded as waves on a string. The strong forces between the particles would correspond to pieces of string that went between other bits of string, as in a spider's web. For this theory to give the observed value of the strong force between particles, the strings had to be like rubber bands with a pull of about 10 tons. In 1974, Joel Scherk from Paris and John Schwartz from California Institute of Technology published a paper in which they showed that string theory could describe the gravitational force, but only if the tension in the string were very much higher, about 1,000 million tons, one with 39 zeros after it. The prediction of string theory would be just the same as those of general relativity on normal length scales, but they would differ at very small distances, less than 1,000 millionth of a centimeter. A centimeter divided by 1 with 33 zeros after it. Their work did not receive much attention, however, because at just about that time most people abandoned the original string theory of the strong forces in favor of the theory based on quarks and gluons, which seemed to fit much better with observations. Scherk died in tragic circumstances. He suffered from diabetes and went into a coma when no one was around him to give him an injection of insulin. So Schwartz was left alone as almost the only supporter of string theory, but now with the much higher proposed value of string tensions. In 1984, interest in strings suddenly revived, apparently for two reasons. One was that people were not really making much progress towards showing the supergravity was finite, or that it could explain the kind of particles that we observe. The other was the publication of a paper by John Schwartz and Mike Green of Queen Mary College, London, that showed that string theory might be able to explain the existence of particles that have a built-in left-handedness, like some of the particles that we observe. Whatever the reasons, a large number of people soon began to work on string theory and a new version was developed, the so-called heterotic string. which seemed as it might be able to explain the types of particles that we observe. String theories also led to infinities, but it is thought they will all cancel in the versions like the heterotic string, though this is not yet known for certain. String theories, however, have a bigger problem. They seem to be consistent only if space-time has either 10 or 26 dimensions, instead of the usual 4. Of course, extra space-time dimensions are a commonplace of science fiction. Indeed, they are almost a necessity, since otherwise the fact that relativity implies that one cannot travel faster than light means that it would take far too long to travel between stars and galaxies. The science fiction idea is that maybe one can take a shortcut through a higher dimension. One can picture this in the following way. Imagine that the space we live in has two and only two dimensions and is curved like the surface of an anchor ring or torus. If we were on one side of the inside edge of the ring and you wanted to go to a point on the other side, you would have to go round the inner edge of the ring. However, if you were able to travel in the third dimension, you could cut straight across. Why don't we notice all these extra dimensions? If they are really there, why do we see only 3 space and other 1 time dimension? The suggestion is that the other dimensions are curved up into a space of very small size, something like a millionth of an inch. This is so small that we just don't notice it. We see only 1 time and the 3 space dimensions, in which space is fairly flat. It is like the surface of an orange. If you look at it close up, it is all curved and wrinkled. But if you look it from a distance, you don't see the bumps and it appears to be smooth. So it is with space-time on a very small scale. It is 10-dimensional and highly curved, but on bigger scales you don't see the curvature or the extra dimensions. If this picture is correct, it spells bad news for would-be space travelers. The extra dimensions would be far too small to allow a spaceship through. However, it raises another major problem. Why should some, but not all, of the dimensions be curled up into a small ball? Presumably, in the very early universe, all the dimensions would have been very curved. Why did 1 time and the 3 space dimensions flatten out, while the other dimensions remain tightly curled up? One possible answer is the Anthropic Principle. 2 space dimensions do not seem to be enough to allow for the development of complicated beings like us. For example, 2-dimensional animals living on a 1-dimensional Earth would have to climb over each other in order to get past each other. If a 2-dimensional creature ate something it could not digest completely, it would have to bring up the remains the same way it swallowed them. Because if there were a passage right through its body, it would divide the creature into 2 separate halves. Our 2-dimensional being would fall apart. Similarly, it is difficult to see how there could be any circulation of blood in a 2-dimensional creature. This is only for the part 1, the unification of physics. See you in the next section, part 2 of the chapter. Till then, stay tuned, take care, bye-bye. Have a great day.